Hi, my name is Ganesh Puvada and I am working as a project manager in one of the leading telecom companies in UAE. As part of AI product management specialization course from Duke University, I was assigned with a project to predict the net hourly electrical power output of a combined cycle power plant. The dataset has 9568 hourly records with four main input features such as temperature, ambient pressure, relative humidity, and exhaust vacuum. The target we are predicting is the net energy output in megawatts. And the goal is to build a model that can predict energy output accurately so that the operators can optimize the plant performance. Since the target output is a continuous variable, this is considered as a regression problem. So to evaluate the models, I selected root mean squared error as a primary metric because it penalizes large errors more heavily. In addition, I also used mean absolute error to measure the average prediction error and of course R squared to measure how much of the variance in energy output is explained by the model. The dataset has four input features, but I also engineered the additional ones. In my first model, which is model 1, I used the original four features. And in model 2, I added engineered features such as temperature squared and temperature multiplied by humidity to capture non-linear effects as well. Both models were built using linear regression in Excel with coefficients estimated through regression analysis. To evaluate the models fairly, I split the dataset into 80% training and 20% testing. For the training data, I applied k-fold cross-validation with k is equals to 5, meaning the data was divided into 5 folds and each fold was used once for validation while training on the rest. This way, I ensured that my results were not dependent on a single random split and I got more reliable estimate of the model performance. These are the calculations done during the output derivations in which predicted PE was derived with intercept plus sum of the product of coefficient and feature. Also, residuals, RMSE, MAE, R square for the train, test and each fold were calculated. Model 1 was derived using the original four features and Model 2 was derived using the added engineered features. This table shows the comparison between the two models. Model 1 with the original features achieved a test RMSE of 4.76, test MAE 3.71 and test R square as 0.92. While Model 2 with engineered features and improved performance has given a test RMSE of 4.42 and test MAE 3.47 and test R square as 0.93. This means that Model 2 predicts energy output with smaller errors and explains more of the variance compared to Model 1. Based on the comparison, I selected Model 2 as the final model because on the test set, it achieved an RMSE of about 4.42 megawatts and MAE as 3.47 megawatts and R square as 0.93. This shows the model can predict within roughly 4 megawatts of the true output while explaining over 90% of the variance in energy output. This is the Excel that was used to derive all the values. So, the dataset 1 consists of the original features and all the calculations were based on the original features itself. Dataset 2 consists of engineered features and the calculations here are based on all the original plus engineered features. So on comparison, Model 2 has performed better. So in conclusion, this project successfully built a regression model to predict energy output of a combined cycle power plant. Thank you.